Hi, I'm Bridget Ratcliffe, and I am a grad student at Columbia University. And I'm going to be talking today about my project, which was recently accepted into APJ, on tracing the birth properties of stars through their chemical abundances. This work was done in collaboration with Melissa Ness, Katherine Johnson, and Bodhi Sen from Columbia, Tobias Buck from AIP, and Victor De Bautista from the University of Central Lancaster. All right, I'm going to start with a very basic background on the stellar composition, just so we're all at the same page, and go from there. So stars are predominantly made up of hydrogen and helium, with traces of what are called heavy elements. And the distribution of these heavy elements is what varies from star to star, depending on the gas from which it formed in. And these are measured in terms of abundances. Star clusters are theorized to be chemically homogeneous, meaning that stars that are born at the same time and at the same place should have the same chemistry. Now, a problem I think we all know about is trying to understand how was the Milky Way formed and how has it evolved over time. And this could best be solved if we knew exactly when and where a star was born, i.e. if we knew stellar age and birth radii. Stars have dynamical memory loss since they move and their orbits evolve over time, meaning that we can't use their kinematics to directly look back and understand this evolution. Instead, we need to look at their fundamental measurements, which are their ages and their chemical abundances. This brings to the idea what's called chemical tagging, which is identifying stellar formation sites from present-day abundances. In order to visually understand this, pretend each color skittle here represents a different birth group of stars, meaning that these are all the yellow stars were born at the same time and at the same place, and therefore have the same chemistry, and these are different than the orange, the red, etc. Now, over time, all these stars move, all these skittles move, and we end up with this current day picture of everything all being mixed. The idea of chemical tagging is to be able to look at this chaotic mixture and pull out which stars were in fact born at the same time and at the same place. So basically being able to look back at this original picture. The main questions that I'm hoping that I will be addressing in today's talk are, is there a relationship between chemical abundances and birth properties? And also, how does the presence of observational error affect the relationship between chemically similar groups and their birth properties? I address these questions by primarily focusing on two simulations, two hydrodynamical Milky Way-like simulations. The first one only traces two abundances, iron and alpha. The other simulation traces 15 different abundances, so lots of information there. Looking at the birth radius and age trends in the abundance plane, we can see these really nice linear trends. And these are important that I will discuss later on, so can you keep these in the back of your mind. In order to determine what is a chemically similar star, which stars are chemically similar, I use hierarchical clustering. And the reason for using hierarchical clustering rather than a different clustering method is that this does not require a pre-specified number of clusters. Working in high dimensions, so in this case up to 15 abundance dimensions, we really cannot visualize what's happening. So therefore, we don't know how many clusters comprise our data. Choosing the wrong number of clusters a priori could give misleading results, and therefore choosing something like hierarchical clustering is playing on the safe side since we don't really know how many clusters to expect and to investigate. One of the things I also really like about hierarchical clustering is that it's very easy to understand. It's a very natural way of combining stars. So how it starts is that each star begins as its own individual cluster, and then at a given iteration, hierarchical clustering just combines groups of stars that lead to a minimum increase in total within cluster sum of squares. At the end, hierarchical clustering gives us what's called a dendrogram, and this is really just a fancy tree-looking object that allows us really to see and understand the structure of our data and how the stars combine. Okay. So, we find that clustering in abundance spaces corresponds to groups of stars that are born at different times and locations. So these middle columns here are an example of what these clusters look like in the 2-dimensional and 15-dimensional abundance space. Then we project these clusters into the age and birth radius plane. And from here, we calculate the percent that these clusters overlap in the age and birth radius plane and project it onto this left figure here. So this left figure here shows the percent that clusters, again defined in chemical abundance space, overlap in the age and birth radius plane as a function of the number of clusters. So a percent overlap of 0% would correspond to groups that, chemically similar groups that are completely different in the age and birth radius plane, whereas a percent overlap of 100 would correspond to these groups completely living in the same areas in the age and birth radius plane. We also find that clusters separate more in birth space and time when using more abundances. So you can see here that when we use for the 15-dimensional abundance simulation, clustering in 15 dimensions, abundance dimensions, creates groups of stars that are born in completely separate areas of time and location for up to about 9 clusters. All right. So, one thing though that you guys might be wondering is, how do I know that this difference is due to the fact of this additional abundance information and not just the fact that I'm looking at a different simulation? By clustering in just the alpha and iron abundance plane of the 15-dimensional abundance simulation, I find that those results are very similar to just clustering in the 2-dimensional abundance simulation, and therefore we can see that the separation in age and R-birth is not an effect of the different simulations, and rather must be an effect of this additional abundance information being brought in. Another question you guys might have is, why bother clustering? Why can't we just grid or bin in the magnesium and iron abundance plane and call it a day? And the reason for clustering is that clustering preserves physical interpretations of these groups, of these chemically similar groups. And we can see this by plotting the mean and standard deviation of each cluster colored by the mean mean iron abundance, where for a given birth radius, we can see this nice metallicity gradient. Whereas when we grid, there is no metallicity gradient to observe. Also, we could see that the standard deviations are smaller, and therefore this shows that when you're clustering, there's less dispersion in age and birth radius than it is with gridding. Now, right now, we've just been talking about simulations and therefore perfect data, and observational data is anything but perfect. So, in order to investigate the effect of observational sample size and error, I recreate observational data of these simulations, where I subsample in 30,000 stars and add either no error, the best case error, or a typical error for a survey. The reason I chose 30,000 stars as my subsample is this is on par with Apogee's red clump catalog. Right. We find that higher dimensional data is absolutely necessary for chemical tagging and its variants if we want to use this on current day observational data sets. I also propose a simple model for modeling current stellar properties and their properties. I use a simple second-order polynomial regression in order to estimate age from their abundances and birth radii from abundances in age. We find that age The precision of estimating age significantly increases with the addition of more abundances, where we are able to precisely estimate age to within 0.06 gigayears in the 15-dimensional abundance simulation. Whereas in the 2-dimensional simulation, we can precisely estimate age by an order of magnitude higher to within half a gigayear. Estimating our birth, on the other hand, does not significantly improve when we include more abundances. And we find that in both simulations, we can estimate our birth to within about just over 1 kiloparsec. Now, as I mentioned, I only use a second order polynomial, so nothing really complex here. And you might be thinking, well, okay, 1 kiloparsec's great, but what if I had done some model fitting, model selection, and picked something more complex? And I propose that I don't think for these simulations that that our birth can be more precisely estimated from abundances in age alone. I find that for a given value of abundances in age, that the intrinsic dispersion in our birth is just over 1 kiloparsec, so almost exactly what I have here, almost exactly what I have with this model. And this might just be due to the fact this intrinsic dispersion of 1 kiloparsec might just be due to asymmetries in the simulations, causing abundance distributions to not lie in perfect annuli about the galactic center, therefore reducing the tightness of birth radius and the abundance relationship. So far I've just been focusing on two simulations that have a similar formation history. And so a very natural question is, well, what happens under a different formation history? So I am showing here a simulation that underwent clumpy star formation. And we can see that the age trends are much different than what I showed, the nice linear trends I showed earlier. We can find that under clumpy star formation for the simulation that we were able to predict our birth from age and metallicity to within 0.7 kiloparsecs. So we are able to predict our birth more precisely for this simulation. However, we find that groups in abundance space no longer correspond to distinct groups in age and birth radius. So you're probably thinking now, okay, I've just been talking about how abundances give us birth information, and now I just said for this one simulation, this is no longer true. You're probably thinking, like, what's the point? Does this relate, is this even useful for the Milky Way? And the answer is yes, it's useful for the Milky Way. In order to understand if we're able to extend these results to the Milky Way, we found that in order for chemically similar stars to correspond to distinct groups in age and birth radius, that they needed low age and our birth dispersions in the abundance planes. So we investigated the age dispersion of the Milky Way and found that it is consistently small, and it is on par with the simulation age dispersions when redrawn from observational error, whereas it is significantly lower than the age dispersion of that clumpy formation simulation that I had just shown on the previous slide. We therefore think that these conclusions that I've been talking about are in fact relevant to the Milky Way. This is exciting, since then we can now link clustering in the Milky Way, and this work can now interpret my previous work from 2020, where I found that 6 clusters, again using hierarchical clustering, this time in Apogee's DR14 red clump catalog, 6 clusters had significantly different ages. We now can go a step further and say that these 6 clusters additionally are from different times in birth time and space. So I just want to quickly go through my main conclusions that I'm hoping you guys can take away. The first is that with just 2 abundances alone, we're able to trace separate clusters in birth time and place, where we have more discrete separation when additional abundance information is included. When simulating observational data sets, we need more than just 2 dimensions. We need higher dimensional abundance data in order to do chemical tagging and chemical tagging variants. And finally, what I last showed is that under certain formation conditions, abundances are a timestamp, when there is an underlying relationship between age, metallicity, and R-birth, we are able to estimate R-birth. However, formation history ultimately drives the ability to reconstruct stellar groups that are born at different times and places from their chemistry. But the most exciting and important result here is that these conclusions we believe can be extended to the Milky Way, and therefore chemical tagging and its variants are possible for our own galaxy. Alright, thank you guys for listening and watching. If you have any questions, I will be in Gathertown, or feel free to email me. My email was on the first slide. Alright, thank you very much.